So the next talk is from University of Edinburgh. The title is a verb lexicon model with source-side syntax context for string-to-tree machine translation. And the work is by Maria Nadeide, Alexandra Birch, and Philip Kuhn. And joint work with Johns Hopkins University. And the talk is given by Maria Nadeide.
Thank you. So I added neural in the title so it fits better with all the rest of the talks. Yes. This work will be about improving verb translation in string-to-tree machine translation. And this is the outline. I will briefly introduce the problem of verb translation in string-to-tree systems. I will then compare our model a bit with previous work on lexicon models. I will then go into the details of our model and show why the syntactic context is beneficial for predicting a target verb. And then I will use our models as an extra feature for re-ranking the output of a string-to-tree system and then evaluate results in terms of translation quality and verb translation quality. Okay, so I will begin with an example for the German-English language pair. All the results are for this language pair, and because there is difference in word order between German and English, so verbs and arguments are reordered, and most often the verb ends up at the end of the sentence. And the way syntax models deal with this reordering is with synchronous context-free grammar rules, which often will translate the verb independently of the arguments, and therefore we have a problem with the verb translation. So I'll go through a small example. So this, the source sentence is the German sentence, which has two clauses, and the reference translation is on the top. Congressmen have proposed legislation to protect union organizing as a civil right. So let's suppose the system has already translated these noun phrases that can be quite complex. And next we want to translate the verb in the second clause, so to establish. And for that we use a synchronous rule, which is written at the bottom. So this rule translates the verb and at the same time reorders it such that it, in the English translation, it comes before the direct object, noun phrase bill. So the rule has a left-hand side, which is, in the case of string-to-tree systems, is a syntactic non-terminal. Here it's an S because it's translating a whole sentence. And the right-hand side of the rule has two parts, one corresponding to the source side span, which is being translated, and then a second part, which is the target side span. And again, for string-to-tree systems, the target non-terminals that appear in the rule have to cover a syntactic constituent, while the non-terminals on the source side can cover any spans of word. So in this case, the translation of the verb is quite straightforward, so the system produces the correct translation. However, we can see that this rule has little lexical context, and the subcategorization frame of the verb is only represented by that syntactic label for the NP. So now we're left with translating only the verb in the first sentence, so haben eingebracht, which should translate as proposed. And note that we've already translated all its arguments independently of the verb. So now we can apply another synchronous translation rule, which this time produces the wrong translation for this context, because in this context, the table will suggest rejecting the bill. So again, note that there is very little lexical context and partial information about the subcategorization frame. So in this work, I show that a verb lexicon model, which has access to the syntactic representation of the source sentence, is able to use all the arguments of the verb on the source side to predict a better translation for this verb. In this case, we have the word congressman in the context, so we can produce a translation, translation introduced. So you want to determine to what extent verb translation is a problem in string-to-tree systems, and what would be the potential impact of a verb lexicon model. So for this purpose, we evaluate a baseline string-to-tree system in terms of verb translation recall. This system is trained on WMT15 data and evaluated on all the verbs from the NEWS 2013, 14, and 15 test sets. So we can see for the one best translation, the verb translation recall is quite low at 45.5%. However, the recall for the 1,000 best list is much better at 72%. So that indicates that there are much better translation options for translating the verbs, and that rescoring the N-best list could potentially result in improvements of verb translation recall for the one best hypothesis. Okay, so there has been quite a bit of work on lexicon models for a phrase-based system. So a discriminative word lexicon model proposed by Mauser et al. Was using all the words in the source sentence as features for a max entropy classifier, which predicted the target word. Extensions to this model include adding target side features, as well as other types of features such as structural features, bag of n-grams, or features extracted from the dependency trees. However, drawbacks of these models are that they train a classifier for each target word or phrase, and they have a very large feature space, well, sparse feature space. Hai et al. Proposed a global neural lexicon model, which is trained with a deep feed-forward neural network, and thus takes advantage of shared parameters, and the model implicitly learns feature combination. This model also uses all the words in the source sentence as input. However, the architecture is more complex, and the model does not scale to large vocabularies. So in this work, we also take advantage of parameter sharing and avoid exploding feature spaces by training our model with a feed-forward neural network. However, unlike the work of Hai et al., we select a global context using the dependency tree of the source sentence and select the context that is most relevant for predicting the target verb. And we train a verb-specific model with the knowledge that verbs have the most outgoing dependency relations, are central to semantic representation, and therefore would benefit most from a source-side syntactic context. So I will now briefly describe how we use a syntactic context and why it is useful for verb prediction. So again, this example, which should translate as congressmen have proposed legislation. In the case of the context for the source verb eingebracht, if we would take a window context centered on this source verb, a 5-word window, we would only able to capture one argument, that's legislation, and a few other words that are not really helpful for disambiguating this source verb. However, if we are to take a syntactic context following the dependency relations in the syntactic tree, we would be able to include all the arguments of the verb, including the word congressman. And moreover, in this work, we also look at other factors, such as including information about the subcategorization frame. In this case, that extra subcat token we use is a concatenation of the dependency relations of the verb. And we also use lemmas in order to reduce data sparsity. So in this example, the input that our model will receive are these 11 pieces of information. So we train our model with a feed-forward neural network using the NPLM toolkit. Our model predicts the target verb given this a wide source-side context. And we compare using a window context with the syntactic context, and we will show in our results that indeed syntactic context is useful for predicting target verb. And in the case of the syntactic context, we will consider the parent, at most 3 dependents, a prepositional modifier, and the particle of the verb if there exists one. And as factors, we explore using just the words or also the lemma and the subcategorization token. So our most complex system could receive so our network would receive a maximum input of 16 tokens in the case of the syntactic context. So our network, our fit-for network is a shallow one. It only has 1 hidden layer and quite a standard setup. We use the rectifier activation function and noise contrastive estimation. And we select the best model out of 25 epochs. Both the source and target vocabularies have 500,000 words. In case of the source vocabulary, the words and the lemma shared the vocabulary. And additionally, we have the vocabulary of the subcat tokens is 80,000. So to evaluate and train our models, we use the WMT15 data. We will evaluate the accuracy of our models on the news 2013, 14, and 15 data. More specifically, we will evaluate verb prediction accuracy. And so we select all the verbs in the test sets. And we only select main verbs determined by the source-side dependency tree, and also restrict only to verbs that align to target verbs as identified by their part of speech. So this way we eliminate some of the noise and we restrict ourselves to verbs that carry more semantic information. So first I begin by showing that predicting verbs cross-lingually is a harder problem than predicting all other words in general. So for this purpose, I train the feed-forward neural network on all the data. So I call this a generic lexicon model. And I train the feed-forward network on all the data and use as input a 5-word window centered on the source word. And then I evaluate the model on predicting all types of words or only just the subset of verbs in our test set. So these results show that verbs are harder to predict, so the perplexity is 2.5 points worse, and the accuracy is almost 7 absolute points worse. So this kind of also motivates our intuition that we should have a verb-specific lexicon model. So next I will show that the verb-specific lexicon model is better at predicting verbs, and also that the syntactic context is more useful than a window context. So this model is trained only on verbs, and we select the source context using a window centered on the source verb. We can see that verb lexicon model trained on a 5-word window is much better than the generic word lexicon model, which is shown on the bottom line. So the generic lexicon model has an accuracy that's 7 points lower than the verb lexicon model. However, you can see that increasing the size of the window for the verb lexicon model does not improve accuracy, and adding extra factors, in this case the lemma, only reduces perplexity but does not improve verb prediction accuracy. So next week, look at how informative is the syntactic context for verb prediction. We see that here a larger context is more useful. So the syntactic context with 7 words already improve accuracy by more than 0.6 compared to the window approach. Then adding the extra lemma factor further increases accuracy and lowers perplexity. When adding the subcat factor, we see that there's only a little bit of improvement, and that is because some of the syntax of the synchronous rules already encode partial information about the subcategorization frame. And finally, when we also add the particle, we get an absolute improvement of about 1.4 points in accuracy compared to the window context. So this confirms that for verb prediction, a syntactic context is beneficial. Next, we want to evaluate how useful the models are for improving translation quality. And for this purpose, we use them as extra features for re-ranking n-best lists. Our baseline system is a string-to-tree system trained on WMT15 data, which we submitted to the shared task. So the results are, again, for translating from German into English. We add 2 new feature scores. One is the verb lexical model log probability aggregated over all target verbs that were produced by the decoder. And additionally, we add a counter for the source verbs that were translated by the current hypothesis. And we add this extra feature in order that our model is not penalized when we score several verbs. So we retune all the feature weights using MERT with the BLEU objective and report results averaged over 3 tuning runs. So this is are the results with evaluating the translation quality with automatic metrics. So we see there's a small decrease in translation quality as reported by BLEU and Meteor when using either of the verb lexicon models. However, we believe that most of the difference is due to fluency being degraded. And of course, BLEU, we're turning towards BLEU, which is a precision metric, while we are trying now also to address the problem of recall. So finally, we also look at inequality of verb translation. And we evaluate this in terms of precision and recall. So we see that both verb lexicon models improve precision and recall. Precision by up to 2.7 points and recall up to 7.4 points. And in case of the more accurate model, the one with the syntactic context, we see that it improves precision as compared to the window context. However, it does not improve recall. So we would need to look a bit more into how tuning towards a precision metric impacts verb recall, and whether we need to increase the model accuracy even more to outweigh decisions that only reward fluency. So I now give a few examples of how the model works in practice. So this is a sentence. The source sentence in this case has a verb with a particle, so the lecten for, and the particle is way at the end of the source sentence. So the verb should be translated as presented. So claimants presented proof of extortion by policemen. However, the baseline model is wrongly translates the verb as went to, and that is because it splits the translation of the verb in 2 parts. First, it translates the main part of the verb with the lexical rule. Well, not the lexical, but anyway. First translates lecten, and then the particle is actually attached to a noun phrase, so it results in a wrong translation. However, when we use the verb lexicon model with syntactic context, we can see that among all the arguments of the verb we can extract from the dependency tree, the particle is also present, and therefore we are able to produce the correct translation presented. However, sometimes we run into problems. So here's another example where one of the verbs in the sentence is mistranslated. So the verb vorgeboren should be translated as charged. Instead, it's translated as alleged. And here again, the verb is translated with the lexical rule, so no other information other than the verb itself. And the verb is then connected with the subordinate sentence using the second rule, which contains the auxiliary to have. So when we use the verb lexicon model, we are able to produce a better translation for the verb, in this case, accused. However, we run into problems with the second part of the sentence. In this case, the second verb attacked is not being reordered as in the baseline system. And that probably happens because the auxiliary verb is, so zu haben, instead of being translated as to have, it's translated as of being. So the second part is not reordered. So this is to show also that while we gain in verb translation accuracy, we sometimes have problems also with reordering. So to conclude, we have proposed a neural verb lexicon model, which predicts a target verb given a wide source-side context. And we select this source-side context using the dependency tree of the source sentence and show that syntactic context is more informative for verb prediction than a window context. Furthermore, we use the models for re-ranking the output of a string to tree systems and showed that it improves verb translation by 2.7 points in precision and up to 7.4 points in recall. However, this improvement is at the cost of a small decrease in BLEU score. However, since verbs are important for semantic representations, and we have quite a big gain in recall, we believe that the small decrease in BLEU score is a good trade-off. And in the future, we would consider improving our model coverage by also considering predicative nouns, and perhaps improving the model accuracy by integrating also target side context. So, thank you for your attention.
Okay, while you're thinking for a question, I have one. So your reference is unique. I mean, you have for each verb. So there could be the chance that your algorithm picks a verb which is correct but doesn't match with the reference.
Yes.
So would it be expensive to prepare a benchmark in which you ask someone to put a list of potential verbs, correct translations?
We were considering doing A/B testing, like just asking the person if they prefer the baseline or our system. The problem is, as I've shown, that sometimes the verb translation improves, but then that results in other more complex rules being wrong. So we might be generating some reordering problems. So I think that would be worth investigating as well.
Okay, but you have two components. I mean, you have the verb selection and then the grammar that builds the sentence. But these are two separate, probably, components.
Well, the grammar includes the verbs, and I mean, the problem is that our n-best list is generating with these rules that translate and reorder at the same time, and sometimes there is not maybe a rule that
there's no coverage for that verb, probably, to build the right construction.
Yes.
Okay.
So, but yeah, it would be worth looking more into.
Okay.
having several references.
Yes, Alon, please.
Precision and recall against the actual verb. So I'm not sure that really the problem is just that the reference doesn't have the right thing. But have you considered doing just an oracle study, basically here? So if you could actually pick, the question is whether in fact you have the right forms in your NBEST list, and then therefore you know the information that this feature is providing should lead you to a better translation, and you're not seeing it in blue. Or the problem is that you don't actually have these good translations, the correct verb translations in the NBEST list. It looks like from the precision recall numbers that they are in the NBEST list, at least in some hypotheses, but those hypotheses might be worse for other reasons. But you could do this basically also by an oracle study. So if you take basically the best, or the oracle best translation in your NBEST list according to the reference and see whether in fact it has more of these verbs that you predict more correctly, for example.
So yeah, I did at some point decode with the system using a language model trained on the actual test data, and I do see in blue score a very big improvement. So, well, it's not as the same as selecting from the NBEST list, but yeah, it should. I should look into that.
So you think it would be reasonable to have a benchmark which focuses on aspects of translation? Let me say, thinking about these potential risk with neural nets that they produce fluent translations, but which are not good in terms of adequacy, having benchmarks that do checks, for instance, that you have correct verb translations?
So yeah, definitely for neural systems, I think yes, there's some bigger problem of just reordering fluency. And well, in Edinburgh, we did work on another semantic evaluation metric, which might be useful for evaluating neural models as well. And I know there's been some recent work that has looked into what kind of syntactic information is implicitly learned by the neural model. So I think it was some work by Kevin Knight's group. So basically, yeah, the neural models definitely include some long-distance dependencies, which can be reflected in this syntactic evaluation. And also, I think maybe Rico Senrich is also looking into analyzing the morphological agreement, which produced by the neural system, which is also dependent on the syntactic relations that are encoded. So, yeah.
Okay, let's thank the speaker again.
Thank you.